다음은 엑슨모빌 업스트림 엔지니어링의 더글라스 페어차일드 선임 고문님의 발표를 듣도록 하겠습니다. 주제는 신개념 고망간강 슬러리 파이프라인 공동 개발 결과입니다. We will continue with our partner's presentation by Dr. Douglas Fairchild, the Senior Welding and Metallurgical Consultant of ExxonMobil Upstream Engineering. The title of his presentation is Newly Developed HMS for Slurry Pipelines. He is already on stage. Please welcome him with a warm round of applause.
Hey, thank you, everybody. It's nice to be here this morning, such a distinguished crowd. Before I get started, I'd like to thank POSCO and Chairman Kwan for the opportunity to tell the story about a new high manganese steel that we've developed in collaboration with POSCO, and also about some of the technology developments for this product that we're referring to as slurry pipelines. And let me talk about the contents of the talk. I'll first give some background information about the Alberta Oil Sands. This is a very large source of oil in North America. It's located in Canada. Specifically, I'll be talking about the Kearl Operation, which is an ExxonMobil partnership. And there you can see the photograph on the right-hand side. The Kearl facility is located there in the background, and there is a critical component to this operation. We refer to them as slurry pipelines. So I'm going to go through some of the basics of slurry pipelines. And then I'll talk about the metallurgical developments for the high manganese steel, the metallurgical concept, laboratory testing. The wear resistance properties of this steel are quite good, and I'm going to talk a little bit of detail about how we engineered that. And then there are some trial spools that we made, trial pipes, sometimes we call them spools, that were field tested. So I'll talk about the results of those field tests, plate development, welding development, and then the current phase that we're in right now is commercial deployment. I'll explain that and then provide a summary. Okay, so what are the oil sands? The oil sands are a mixture of sand, rock, water, and bitumen. It's a heavy oil product that we refer to as bitumen. You can see they're being held in the hands. And these deposits are located in Alberta, Canada. You can see the highlight there. And those orange areas are the oil sands deposits. So you might ask, well, how much oil is actually there? It's quite large. 96% of Canada's oil are located in these oil sands. Now, Canada, maybe this isn't well known outside of the oil and gas industry or outside of North America, but Canada has the third largest oil reserves behind Venezuela and Saudi Arabia. So Canada certainly plays a role in the global oil and gas market. Here is a graph showing major new liquids finds in North America, millions of oil equivalent barrels on the y-axis, time projections on the x-axis, and you can see out to 2040, those oil sands are predicted to be a very major source of oil for North America. So how is the oil recovered from the oil sands? There's generally two ways. If the bitumen, if the oil sands are below the surface, maybe a few hundred meters, then drilling, referred to as the in situ method, is used for extraction. But if the oil sands are up close to the surface, then they are mined, and the mining only takes place in Athabasca, which was that large orange area on the Alberta map I showed just a minute ago. So this is the Kearl Operation, which is an ExxonMobil partnership with Imperial Oil and ExxonMobil in joint ownership. And here's a cartoon that describes the oil sands operation. They're first mined by scooping with shovels, placed into trucks, taken to a crusher where it's reduced to smaller particulate size. It's then sent into a mixer, and it's mixed with water, and then that first arrow that you see there, that is a slurry pipeline, and it's taken over to an extraction plant. There are some slurry pipelines after the extraction plant as well, but the extraction plant is where the oil is removed from the ore. To give you an idea of the scale of the operation, you can see some of the mining equipment here. And if you look at the individual workers in those photographs, you can get an idea of how large this mining equipment is. The shovel there, 120 tons per scoop, and 120 tons, to give you a scale idea there, that's about the size of a heat of steel from Pohang Works. But these shovels, they remove a scoop every few minutes. Then the trucks, also very large, they take them over to the slurry preparation area. Here's a couple of photographs of the slurry pipelines. And notice that in these slurry pipelines, there are a number of flanged connections. I'll explain the reason for the flanging here in just a minute. Here's a photograph of the extraction plant, very large facility. And to give you a better idea of the scale of the operation, here's some more metrics. The Kearl project, the CapEx, the capital expenditure, has a $22 billion price tag. It covers 200 square kilometers. It started producing oil in 2013, and the projected service life is about 40 years. If you look at the graph here of the estimated production from the Kearl operation, the y-axis shows thousands of barrels per day, and the time projection is shown on the x-axis. So 350,000 barrels per day, and so as I said, it's a very significant source of oil for North America. So now let me talk a little bit about slurry pipeline basics. Let me talk what goes on inside the slurry pipeline. And there, with the simple animation, you can get an idea of the transport of this sand, rock, water, and bitumen product. The rocks inside this pipeline are up to 125 millimeters. That's about the size of your fist, or maybe a little larger. So there's some very large erodent materials inside this pipeline. There's damage going on inside the pipeline, and specifically at the 6 o'clock position, we have maximum erosion, and that's where the erodent material, the sand, the rocks, it settles, it bounces along the surface of the pipeline, and it removes material. Now, that erodent material doesn't contact so much the 12 o'clock position, so we have primarily a corrosion mechanism that is dominant there. There's water, there's oxygen inside the pipeline, so certainly there is corrosion. Here's a cross-section photograph near the seam weld of the slurry pipe, and there's nothing special about this seam weld. It's only there to visually demonstrate what happens when this erosion takes place. You can see here is an example of 50% wall loss. These pipelines are operated until just a few millimeters exist in the pipe wall, and then they are retired. They're scrapped. The traditional material for these pipelines is API 5L X70. The pipes, I should mention, they are periodically rotated to move that 6 o'clock heavily eroded region away from the 6 o'clock position. So every few months, the pipelines are unflanged, and that's the reason for the flanged connections that I mentioned previously. They're unflanged, rotated maybe a third of a turn or a quarter of a turn, bolted back together, operation continues. But even with that, the X70 pipe service life is only about 1 year, and then the pipelines have to be replaced. So let me talk a little bit about the high manganese steel pipe development, this collaboration with ExxonMobil and POSCO. We started this work in 2009. Why did we collaborate? It's fairly simple. ExxonMobil needed better pipe. POSCO are expert in high manganese steel, which has very good wear-resistant properties for certain grades, and both have world-class materials engineering skills. Korean, English is no problem when you both speak materials science, so we're able to work well together. Here is a general idea of the development steps. First, the chemistry formulation. The chemistry is about 1% carbon, 18% manganese, a number of other alloys. Chrome you can see there for the corrosion resistance. And we conducted a lot of laboratory trials, made many lab heats, studied the processing, the heating and cooling, and the rolling of the material, and then measured basic properties like strength, toughness, hardness, corrosion, and erosion resistance. We had a laboratory test to measure the erosion resistance. You can see there the pumping of a slurry jet. This is water mixed with sand product that impinges on the test coupon. And then the coupon there shown on the right, you can see that impingement area, and the basic metric measured in this test is weight loss. And here you can see weight loss on the y-axis and a number of the alloys, the experimental laboratory alloys on the x-axis. And down there on the right-hand side, X70, that's the traditional grade for slurry pipelines, and the high manganese alloys are performing much better than the X70. And so in the end, we selected a champion chemistry and processing route and have scaled it up to commercial production. Now let me talk about the mechanism of wear resistance in these high manganese steels. Now, high manganese steels is a rather large family of steels, but there's a particular chemistry formulation, a particular grade that's rather good for wear resistance. So you can see there the cartoon cross-section of the pipe wall and then some erodent material like sand or rock. What happens when this particle strikes the surface is that a small region, and let me just show that one more time, a small thin region underneath the material that's removed, the impacted area, it goes through metallurgical transformation and it undergoes a nanocrystallization event, and the grain size is extremely small in that thin layer. The average grain size is about 10 nanometers, and so you can imagine the continual process here inside the slurry pipeline as the material wears away. Yes, material is physically removed, but at least there's a thin layer underneath the surface that transforms very fine grain and has better wear resistance. In this regard, you can refer to this material as a smart material because it's having a positive reaction to the service environment. We've done a lot of microscopy. Frankly, I could stand here all day. I'm a metallurgist. I'm a welding engineer by training. I'd love to talk about the electron microscopy and some of the material science, but we'll save that for some publications in 2017. But just understand that we have verified this nanocrystallization event through transmission electron microscopy. You can see the layer there. You can even see, for those metallurgists, that there are some microtwins forming just below the nanocrystalline layer, and that's part of the process. This is a metastable material, at least to the erosion resistance, and it is formulated to react to this service environment. We made some trial spools, some trial pipes. These pipes, 4 test spools manufactured in 2013. They were about 3 meters long, and they were 24 inches in diameter and 30 inches in diameter. That's 0.6 meter and 0.75 meter in diameter, and they were installed at the Kearl Operation in 2014. You can see there a picture of a ExxonMobil engineer and a POSCO engineer at the Kearl site. And then notice the high manganese steel test spool there. There's a number of flange locations adjacent to the high manganese steel spool. I'll explain that in just a second. So the scope of work, there were 2 locations in 2 pipelines. Now these slurry pipelines, they cover many kilometers, but what goes on inside the pipelines varies from meter to meter and kilometer to kilometer. The ore, the breakup of the ore, the temperature, the pressure, the flow rate, it all changes in the slurry pipelines. So we had to insert these spools in several different areas so that we were sure it would perform satisfactorily. They were installed adjacent to other candidate materials. That's why all of the flanged connections in that photograph up to the right. There's a lot of candidates vying for this market. X70 was also included for comparison. They were operated for about 1 year, and the wall loss was monitored by ultrasonics, and then once they were removed, physical measurements were used to prove up the ultrasonic measurements. And so here's some of the results. On the y-axis, we have average wear rate in millimeters of materials lost per 1,000 hours of service. And then the circumferential position, the o'clock position on the x-axis, you can see 2 lines. One's high manganese steel, one is X70. At the 6 o'clock position, where erosion dominates, you can see that high manganese, yes, there is some wear, but it's performing much better than the X70 material. And then where corrosion is the dominant mechanism, over at closer to the 12 o'clock and a little bit adjacent to that, the high manganese steel is barely seen any wear at all after 1 year of use, performing very well. We conducted a life cycle cost analysis looking at all the factors, the cost of the material, the maintenance of the material, and our conclusion was that high manganese steel, this particular grade, was superior to all of the other materials tested in this field trial. High Manganese Steel Plate Development. Now, POSCO could really tell better details here, and I would say again, stay tuned, 2017, there will be more publications. The laboratory trials were 2009 to 2011, commercial mill trials, a little bit of scale-up, 2012 to 2013, and the commercial phase is where we are now, 2014 to 2016. This is a continuous cast product. It's produced in slabs. Both Pohang Works, Guangyin Works have produced this material. You can see there a stack of high manganese steel slabs on the right-hand side and the finished plate, the left-hand side, and the finished plates there on the right-hand side. So let me talk about field welding development. Of course, if you're going to take this material to the field, do a big operation, welding has to be supported in the operation. So the welding scenarios that we looked at, primarily two welding procedures. First was just pipe girth welding, butt welding as we call it. And then the second procedure was the welding of carbon steel rings to the ends of the pipes. These rings allow the flanged connections to be made, and that's a dissimilar metal weld. So the welding process is mechanized metal core arc welding. That's essentially gas metal arc welding, except with a cord wire. And the second one is, in fact, a dissimilar metal weld, and all of these welding consumables were produced by POSCO. So let me go through a few other of the scopes of the items of the scope of work. Consumable formulation and wire manufacture, again, by POSCO. Fume and safety analysis. Yes, the material has an elevated level of manganese, so you have to be careful about the fume, but we've done complete studies on that. And in fact, you can see there the welder in the center photograph has a ventilation, positive ventilation device on the back of his helmet, but we've taken care of the fume and safety analysis. Welding procedure development, all the volts, amps, travel speed, we determined that in the research lab and have now scaled it up. Solidification cracking, this was a big challenge. This is an austenitic material. It's similar in welding to stainless steels, to nickel-based alloys, so there are some challenges with hot cracking prevention. But it's very important that the welding consumables used in order to prevent hot cracking are quite pure. So I will mention in the status that the welding consumables manufactured by POSCO, specifically by POS Welding, very pure. They were dedicated to this particular development, and they have performed well. We have been able to mitigate hot cracking. All of the mechanical property targets have been met, and the procedures have been successfully qualified. You can see some photographs there from our ExxonMobil lab in Houston and some contractor welding qualifications up in Canada. Commercial deployment, which is the current period that we're in. 1.2 kilometers of this pipe has been manufactured, delivered, and installed at Kearl. The scope of work has incorporated all of the specifications necessary, pipe specifications, welding specifications, and those are going to be deployed to industry so that other people, other customers can use this material as well. Commercial plate and pipe making, weld consumable manufacturing, double joining and flange ring welding, and then field installation. And here's some photographs from some of the commercialization activities. Pipe making, Sia Steel in Pohang produced this pipe by the JCO pipe making method. Here's some work in Canada where some of the pipes were double joined through girth welding. There's some photographs ready to install. Here's field installation. One thing I'll mention, that photograph on the left-hand side is a plasma cutting operation. This material, as you can imagine, doesn't like to be machined and it doesn't like to be ground. So plasma cutting operations are very important to use with this material. The side boom tractor that you can see there lifting the pipe, those are the same side boom tractors that are used to rotate the pipe. It is anticipated that this material as well will be rotated to maximize the life, and it's anticipated that this high manganese steel will be in service for many years to come. So all of the tasks have been completed and the pipe is currently in service. So here's a summary and current status. So we've developed a new high manganese steel slurry pipe. It's been developed through collaboration between ExxonMobil and POSCO. All of the technology steps have been taken care of: steel, plate, and pipe making, the welding technology, specifications necessary for commercial use, and yes, those will be provided to industry for further commercialization. There's 1.2 kilometers currently operating at the Kearl operations in Canada. We'll have some publications in 2017 to talk about that operation. And so with that, I'd like to say again, thanks for the opportunity, and we've got a relatively good success story here, and I'm glad to share the story with you here today.
네, Fairchild 고문님 감사합니다. Thank you very much, Dr. Fairchild, for your informative presentation and for that detailed explanation on the successful outcome of the ExxonMobil and POSCO partnership.